Hi everyone. From this lecture 10, we simulate a long channel MOSFET. Today, a MOSFET structure is generated and the equilibrium solution is obtained. Before starting today's lecture, a way to monitor a vertex variable is presented. In other words, now your CSV file can have extracted vertex variables. Since it is related with a CSV file, the book statement is modified. Previously, event had only the contact option. Another option of event is vertex variable. By specifying vertex variable, region, and position, we can print the vertex variable at the specified position. In this example, we print the electrostatic potential at two positions, one at the interface and one at the end of substrate. The difference between them is the surface potential. After finishing the last homework successfully, now you have the raw data. Or in our training server, you can directly start the MATLAB. By using the raw data, you can draw the semiconductor charge as a function of the surface potential. Since we have all four quantities to calculate the semiconductor charge and the surface potential, you can draw it. Moreover, you have the analytic relation between Q sub S and phi sub S. Now, a long channel MOSFET structure is generated. It is a planar device. Therefore, instead of the full three-dimensional simulation, we will perform the two-dimensional simulation. The width specified by the area factor is 1 micrometer. These are important parameters of our model MOSFET. Its oxide thickness is 1.2 nanometer. The metal gate work function is 4.3 electron volt. The substrate doping is 1.5 times 10 to the 18 per cubic centimeter. VDD is assumed to be 1.2 volt. The source and drain regions have junction depths of 12 nanometer. The constant N-type doping density is 10 to the 20 per cubic centimeter. The silicon substrate is 120 nanometer thick. For this long channel device, the gate length is 1 micrometer. Later, we will reduce the gate length to generate a short channel device. Now we must discretize the simulation domain. Spacing along the vertical direction is 1.2 nanometer. This value is selected to discretize the oxide layer. Spacing along the lateral direction is 5 nanometer. Then, how many points? We have 102 points in the vertical direction, 221 points in the lateral direction. The total number of grid points is more than 22,000. Of course, it can be simulated, but there are too many points for such a simple structure. We will revisit this issue again. Also, a constant box-like doping profile is assumed for the source and drain regions. It is not realistic. This issue will be revisited too. This is the input file for our model planar MOSFET. The two-dimensional simulation domain is declared by the rectangle statement. You can find that we have no specification about the g-coordinate. It is quite natural because we are now talking about a two-dimensional structure. Contexts are defined in these lines. The generated structure is shown in this slide. As you can see, it is not very realistic. An abrupt box-like doping profile for the source and drain regions, a constant substrate doping, lack of the nitride spacer, positions of the source and drain contacts. These are not realistic, but this structure is sufficiently good enough for the very first simulation. We will improve the structure in various aspects in the following lectures. As the first step, the equilibrium solution is calculated. Although the equilibrium solution can be calculated without specifying the circuit specification is explained in this slide. The MOSFET has 4 terminals. Also, at least 2 independent voltage sources are connected even when the source and body contacts are grounded. Therefore, in this example, we introduce 2 voltage sources, VG and VD. They are connected to the in node and out node respectively. The hole density at the 0 gate voltage is shown in this slide. The red color represents the hole density close to the p-type doping density. We can clearly see the depletion layer at Vg equal to 0 volt. That's it for this lecture 10. We have a model MOSFET. In the next lecture, we will study the input characteristics of this MOSFET. Thank you and see you later.